The preceding lecture covered the statistics used to describe the results from a sample. In this lecture, I'm going to cover the statistics used to assess specific questions that can be framed as hypotheses. Most of these hypotheses are about differences between groups or differences between conditions. So all of these statistical tests so far have compared only two groups, with the exception of the chi-square test of different proportions, which allows testing of 3 or more categories. But tests of mean scores, t-tests, can be done only across 2 groups. Often researchers are interested in comparisons across 3 or more groups, and that comparison can be done with analysis of variance. So to position this, review what t-tests do. T-tests comment on the likelihood that 2 sample means come from a common distribution. So looking at my crude figure here, we've got one distribution, x1, with a mean of 2.2, and a second distribution, x2, with a mean of 5.8. And if we put them all together, we'd have an x total distribution with a mean of 4.0. So the t-test is asking the question, do the means 2.2 and 5.8 represent samples drawn from the same distribution with a mean of 4.0? Or what's the likelihood that those two means would show up in samples that were drawn from a common population? Well, if you think about the computation for the t-statistic, we know that in the numerator, it's the difference between the 2 samples. So the further apart the sample means, the less likely that the difference will be perceived to have come from a common sample. So if we had 2 samples with means of 1.1 and 6.9, that would still have a common population with a mean of 4.0. But now the 2 sample means would be further apart, so it would be less likely to conclude that they came from a common population. So because the t observed in this case would be higher. And the lower the sample variances, the less likely any difference between their means is to have come from a common distribution. So if we went back to our original samples with means of 2.2 and 5.8, and now reduced the variances, so we had the same means of 2.2, and if you look at the right-hand figure here, you'll see our underlying distributions x1 and x2 with the same means, 2.2 and 5.8, but now they're much narrower. So there's less variance in those populations. And so it looks less likely that those populations would have been drawn from the common population with a mean of 4.0. So t-tests consider both the differences between the sample means and the deviations or the dispersion of points within their samples. Well, analysis of variance does the same thing. Analysis of variance is used to assess the equivalence of 3 or more means, that is, 3 plus groups on one measure. Analysis of variance examines each data point in terms of its deviation from the group mean and the group's deviation from the overall mean. So now I've got a figure with 3 sample distributions, x1, x2, and x3, here with means of 3.0, 3.4, and 3.9, and they form an overall population with a mean of 3.4. So ANOVA asks the question, well, what's the likelihood that I can explain a value in the x1 distribution in terms of its deviation from the x1 mean and its deviation from the x total mean? Statistically, that question is framed in terms of partitioning. So ANOVA poses the question, can a significant portion of a score be explained by its group membership? So it partitions the score into a deviation from its own mean and that group's difference from the overall mean. To illustrate this, assume we had 100 cars, and each car was a Honda, a Lexus, or a Mercedes. And every Honda cost $20,000, and every Lexus cost $40,000, and every Mercedes cost $75,000. Well, in this case, if you knew which group the car fell into, you would know its price. Even though there's variance across the total population, there's no variance within the group. So knowing the group would give you a perfect indication of what the car's price is. Now, of course, in most cases, groups have more variance. They have some variance. So the question is, does knowing the group that a score comes from tell you enough to help identify what its score is going to be? So the answer to that question is dependent upon the difference in the average scores in the groups and the variance within the groups, just as it was with t-tests. The further apart the means and or the lower the variance within the groups, the more likely t was going to be large enough to conclude a statistically significant difference. It's also true for ANOVA. ANOVA considers the difference between groups as explained variance. That is, the group membership explains the score. So knowing that a car was a Honda explained that the score was going to be $20,000, the price of the car. Differences within the group are considered error or unexplained variance. And a higher proportion of explained variance to error leads to a conclusion that group membership is useful as a predictor of scores. And that means a statistically significant difference among the groups. These are the mathematical expressions for partitioning error for analysis of variance. The sum of squares total is partitioned into sum of squares within and sum of squares between. Sum of squares, of course, is the sum of the deviations, xi minus x total. So this is the individual score compared to the overall mean, that quantity squared. And that can be partitioned to deviations within the group, which is xi minus xj, which is the mean of that group, squared, and the sum of the differences between the group's mean and the overall mean, xj minus xt, the quantity squared. And if we take a proportion of that sum of squares between and sum of squares within, sum of squares between groups, remember, is the explained variance, the amount that's explained by being in a group, and divided by the unexplained variance, which is the sum of squares within the group. And then we divide each of those, the numerator and denominator, by their degrees of freedom. We get the mean squared error between and the mean squared error within, and that proportion is f. And f is the test statistic for analysis of variance. So what's important to know conceptually here is that as the size of the difference between the groups on average increases, the numerator will go up. And as the average variance within groups decreases, the denominator will decrease. And both of those will lead to a higher value of f, a higher observed statistic, and more likely the conclusion that the groups do not come from the same population. That is, the groups do differ. So the f-test, again, is the mean squared error between divided by the mean squared error within. It's distributed across k minus 1 and n minus k degrees of freedom, where k minus 1 again is the k for categories, the number of groups. So if you have 3 groups, that's going to be k minus 1, 3 minus 1, 2, and n minus k, where n is the total sample size minus the number of categories. F is larger when the group means differ more, and smaller when the overall sample variance is higher. An f-test indicates that, this is important, an f-test addresses the question, the null hypothesis, that all group means are equal. So a positive or significant f-test indicates that not all group means are equal. It does not tell you that the highest of the group means is in fact higher than any of the other group means. It doesn't answer questions about pairs of groups. So if you do an f-test over 3 groups, typically you'll follow that up with pairwise t-tests to address the question of which is the highest or which is higher of any pair. So here we have an illustration of analysis of variance with cars again, but this time looking at the incomes of buyers of 3 brands of cars: Hyundai, Mercedes, and Acura. And the research question is, does car group membership predict income? If we know what group a person is in, do we have a better estimate of that person's income? So we've got 3 purchasers of Hyundai with incomes of $60,000, $55,000, and $30,000. We've got 3 purchasers of Mercedes with incomes of $165,000, $140,000, and $150,000. And 3 purchasers of Acura with incomes of $90,000, $70,000, and $40,000. And again, conceptually, we're looking at the variance within those groups as unexplained variance, and we're looking at the deviation of the means of those groups from one another as an indication of explained variance. So we can see the means within the groups. The mean for the Hyundai owners is 45,000. The mean for the Mercedes owners is 151,667. And the mean for the Acura owners is 66,667. It looks like those, and then the overall mean is 87,778. It looks like the means are fairly different. So the question is, how much variance is within the groups? Well, if we calculate the f-test, we see that we have an observed f of 68.66, and f critical for 3 groups and an n of 9 is 5.14. And since the observed f is greater than the critical f, we can conclude that there is a statistically significant difference in the incomes depending on which car they purchase. So again, we do not know that the income of Mercedes owners is statistically significantly higher than the income of Acura, although I would presume that that is the case. In order to answer that question, we'd have to do a t-test comparing the $151,667 mean with Acura's $66,667 mean. And we can do t-tests across any two pairs, or any pair of these three.